I think let's just begin. So, good evening, everyone. Today's journal club will be going into abstract algebra a little bit. So, before going into the next chapter of Nelson and Chuang, whereby they go back to like your quantum logic gates and so on, I feel like is perhaps a little bit better if we know a little bit of this abstract algebra. I will probably just cover through very quickly all the elements of abstract algebra, and then hopefully I want to go to these two groups, SU2 and SO3, so that you guys can understand the relationship between your unitary matrices on a single qubit and how it affects your rotations on your block sphere. So this will be the target for the next, I think at least next two uh, journal clubs before we go back into Nelson and Chuang. So just a very quick introduction. So we basically probably know what is a set. A set is just a collection of objects. They don't necessarily have any mathematical definitions. So you just try to collect objects that will be of the same kind of properties or structures. So that's the very easy definition of a set. It's just a collection of objects that it may or may not have additional structures. But of course, for us, we will be interested mainly on mathematical objects with additional structures. So, what is a group? So, a group is basically a set whereby you have all these what we call as a group elements inside a big set. So the group elements, you also have what we call as group operations. So your group operations are basically for the group multiplication, we use the notation of dot. So it satisfies what we call as the four group axioms. The first one is called closure, whereby if you take one object from your group, another object from a group, the multiplication between these two objects will again go back inside the group. So if it go outside of the group, then it is not closed under your group multiplication operation. So the first property is what we call as a closure property. The second one is what we call as associativity, whereby when you perform group operations, let's say you have three group elements and you want to multiply them together. So the order of your multiplication does not matter under associativity, meaning that you can multiply the last two terms and then you multiply after you get, let's say this is GL. So then you multiply GI and GL. So this would be the same as when you multiply the first two. Sorry, this should be K. Then you get, after that you multiply with GK. So this is a typo, this should be K. So that's the second property of a group, associativity. The third one basically is the existence of identity, meaning that for whatever group elements that you have, basically you should identify one of the elements, let's say G1, when you multiply with whatever group elements that is. So whether you multiply from the left or from the right, it will give you the same elements, GI. And the last one is what we call as the inverse, whereby let's say your GL is the inverse of GK, then no matter you multiply from the left or from the right, it will give you your identity elements. So basically, you can try to derive the third group axioms. You can derive the fourth group axioms from the third one, but just for the sake of at least we are not trying to be too mathematical. So basically just list it as one of the group axioms. So what would be the examples of a group? The easiest one is the set of all possible permutations. Uh, so let's say you have 4 points, 1, 2, 3, 4, and you try to study all the possible permutations between these 4 points. So you will have 4 factorial of elements, and this group, when you collect them together, this is called a permutation group, P4. So like for instance, if let's say this is your 4 points, 1, 2, 3, 4, and you try to permute between these two. So usually this is what we call as the P12 element. So the way you write your permutation is basically something like this. So the top part will be your original permutation, so to say, and you try to map it to 2, 1, 3, 4. So you are switching the element of 1 and 2. So if let's say you have something like this, so you are switching these two, but the first element and the fourth element will be the same. Then you will have 1, 2, 3, 4, and then 1, 3, 2, 4. Okay. So what would be the group operations for the permutation group? For instance, if you want to multiply P12, P34, so you don't multiply as a matrix because this is basically telling you how to permute your elements. So even though you write it in some way like a permutation, like a matrix, but this is not actually a matrix. So the way for you to do that is to write the first element, and then in this way, 2, 4. So now the easy part that I find like easier for you to understand is to try and copy from the first sort of like matrix 2, 1, 3, 4 to match to the top part of this. Essentially, what you're trying to do is let's say you have 1, 2, 3, 4, 1, 2, 3, 4. You apply the first matrix or first permutation on the right, then you apply the second one. But the easier way for you to do it is to do it this way without like trying to figure out how the elements are permuting towards each other. Like you need to write down 1, 3, 2, 4, and then you need to permute between these two again because of P12. So this first step of permutation is P34. Then you have a second permutation P12. So mathematically speaking, it's easier for you to do it this way. So you write 2, 1, 3, 4. So now on the top of the second matrix, so to say, you try to refer back to this particular table. So 2 maps to 3, 1 maps to 1, 3 maps to 2, hello, and then 4 maps to 4. So once these two are the same, then you basically can copy down your final answer. Someone is not muting yourself. And you can see that this is precisely what I did. So first, you have 1, 2, 3, 4 as your permutation. And then you perform P34. It becomes 1, 3, 2, 4. Then the second step is to perform P12. So you get 3, 1, 2, 4. So this is a result of these two permutations, P34 and then P12, 3124, and this is 3124. So that's how you perform group multiplication inside a permutation group. If you have any questions, you can ask, because this is quite mathematical intense, at least for the next. So basically today I'm going through abstract algebra. The next week journal club I should go through what is SU2 and what is SO3. So why do I focus on SU2 and SO3, and why should I go through linear algebra or abstract algebra? Because this is essentially your quantum logic gates, your unitary matrices. At this point, if you don't have a little bit of knowledge on group theory, I think it's very difficult to continue on. Otherwise, you'll be just having a surface level of understanding of how the logic gates behave. Whereas for SO3, this is basically your symmetry or geometry of your block sphere. So without understanding the correlations between your SU2 and SO3, is kind of difficult for me to continue keep giving you all these different relationships between SU2 and SO3, like in the Nelson and Trong book. They kind of assume that you know part of this. So that's why I go through abstract algebra and then the group structure and the Lie algebra structure of everything before I go back to Nelson and Trong. So coming back to this example 1. So basically P4 is a group with all the possible permutation, and the way you define your group multiplication is very much defined. This is the way you should define your group multiplication. So mathematically speaking, you can do this particular step that I did, or you can try to start with 1, 2, 3, 4 as your initial permutation, and then you slowly perform all the permutation required, P34 and then P12, to get the final results. So that's the first example of a permutation group. The second one is another easy one. Basically, it's just a rotation of a circle. So let's say you have a circle and you divide each of these rotation to be 2 pi divided by n. So every time when you rotate 2 pi divided by n. So because your rotation is kind of like a fixed element, every time you can only rotate 2 pi divided by n, this should be a finite group. At this point, I did not define what is a finite group, what is a continuous group. So now I will define it. So finite group basically means that your group elements, you can count it. So like the first example, your permutation group by itself is a finite group. And the second example, just a rotation of 2 pi divided by n, because at most you will have n points, right? So there's only n times you can rotate on a circle. So that's why this is also a finite group. Each rotation will take you 2 pi divided by n, and you will have only n distinct operations. So whenever you talk about finite groups, you talk about the number of group elements. So in this case, your order is n, meaning you only have n elements inside your finite groups. So this is a bit easy, and I think in terms of the group operations, basically it will be something like this. So every time when you rotate, so let's say your circle is of r equals to 1, then every time you rotate, you actually act with this kind of elements. So it's well defined because it's just a multiplication of your exponentials. The third example is quite similar to the second one, whereby you try to rotate on your circle, but this time you don't limit your rotations with finite kind of rotations. So this data is becoming like a continuous number between 0 and 2 pi. So then this is what we call as a continuous group. And the group operation is basically just ei theta. And you have a one-to-one correspondence with points on this particular interval. So I will explain what is this one-to-one correspondence later on. But basically what it means is that if let's say this is your rotations ei theta, then basically your rotations is correlated to your theta. So your theta, if you notice, let's say you have R1 element and you have R2 element. So you notice that when you try to do your group multiplication together, R1 multiplied with R2, it becomes like a summation on top. And this is what we call as the one-to-one correspondence. So you are corresponding your rotation to the summation of two parameters, theta 1 and theta 2, on these particular intervals. So that's the third example. So what would be other examples that we are familiar with? So let's say you have some real numbers or complex numbers. So let's say real numbers. When you exclude 0, it forms a group under multiplication. So you can try to verify this. It will be the same as with your complex numbers. There's another, I think there's another one called the quaternion, but I don't want to go into that at this point. So let's just focus on the real and complex numbers. When you don't include 0, it actually forms a group under your multiplication. Whereas if you use your addition and you include 0, then your real numbers with addition is also a group. So what would be the identity element for example 4? The identity element will be 1 because you are acting with multiplication. Whereas here the identity element will be 0. And 0 cannot be included inside example 4 because 1 divided by 0 is not defined, which means that your 0 does not have the inverse. Okay, so that's why 0 cannot be included in example 4, but if it is addition, then you can include 0. And 0 is your identity element. So the next example, example 6, probably is the most important examples across what I want to discuss. It is the set of all non-singular matrices under matrix multiplication. They actually form a group called the general linear group. N means that you have n dimensions. R over here means that your entries are real numbers. So if you notice, let's say you have let's just try some very simple examples. So if this is non-singular matrix, and let's say you have real numbers, so no matter how you multiply, let's say 5, 6, 7, 8. So when you multiply these two together, you will produce another matrix, which is non-singular. And yeah, the basic requirement is non-singular. So it doesn't matter what kind of matrices you try to multiply, as long as your matrices are non-singular, you always get back a non-singular matrix. And your group operation is matrix multiplications. So if you want to consider a subset of these matrices, you can consider matrices with determinant plus 1. they will form a subgroup, meaning that your GL is a bigger group, and then you have a smaller group called SL. So this smaller group, when you try to do like matrix multiplication, and between two matrices with determinant plus one, they will always form back inside the SL groups. That's why this is a subgroup called SL and R. SL means special linear. Again, n is your dimension, R is the entries of your matrix elements, which is real numbers. So the third type of example would be unitary matrices. So over here, unitary matrices, I don't really care whether or not your determinant is plus one or minus one. I just want unitary matrices. So as long as you satisfy U dagger U equals to identity, or UU dagger, perhaps I write in this way. As long as you satisfy this condition, then basically it falls under UN. So it also is also a group under matrix multiplication, because no matter how you multiply the unitary matrices, you get back the unitary matrix. What else? Yep. I think so far that's what I want to say. If you want to fix your determinant of U to be plus one, then this becomes special unitary group of dimension n. So when I say SU2, it means a special unitary group of two dimension, 2 times 2 matrix. So if let's say your group obeys a fifth group axioms, so this is not you don't necessarily need to obey this, but if you obey this fifth axiom, which is commutativity, meaning that you take two group elements, you try to switch around the position, and you find that they are the same, then they are commutative. Okay. So which of these examples are abelian group? So you can call them abelian group or commutative group. So which one of these would be abelian? You have 6 examples. Is the first one abelian? Anyone want to unmute yourself and say the answer?
I don't think so.
Okay, the first one is not abelian. How about the second one?
Yes.
Second one is
Oh.
abelian. The third one?
Yes.
The fourth one?
Fourth one, yes.
Yeah, multiplication in real numbers should be abelian. 1 times 2 equals to 2 times 1. Addition?
Yeah.
Yes.
Number 6?
No.
Whatever matrix group. Usually it's no.
No.
Okay. So yeah, that's on the groups. Later I will come back to the groups, but now let's introduce what is a field. So a field is basically another set, F0 until like whatever. So now you have two operations. The first one is what we call as addition. The second one is scalar multiplication. In such a way that when your when your field F, the set F, together with addition, it forms an abelian group. And your F naught, let's denote it as your identity. Whereas the rest of these conditions closure, associativity, identity, uniqueness of inverse and distributive law. They correspond to scalar multiplications. So the first one is, of course, when you do your scalar multiplications of two field elements, they should be inside the field. The same thing over here, they should be associative. And then you should have identity and the inverse should be unique. What is perhaps more interesting is how your scalar multiplication is distributed inside your addition. So over here, if let's say you have one field element multiply with scalar multiplication with the addition of these two field elements, you just multiply accordingly. Or if it is in this form, then you just multiply accordingly as well. So that's your distributive law. So again, the same thing. If you satisfy your commutativity, then basically your field is commutative. So for physics, we basically just use these three fields. But if you do error corrections, you will also encounter what we call as the finite field. I will go into that when we need it, but right now, the three fields that we generally use is the real numbers, complex number, and quaternions. Don't bother with quaternion for now. If I want to talk about these three things, it will take another hour to do so. So let's stop for now. We just want to focus on real and complex for now. So then what is a linear space, vector space? A linear vector space, basically you have a set of vectors. So now you have sort of like two things in one. You need to specify your vectors and you need to specify what is the field under going over your vector space. So these two sets, how are you going to match sort of like between each other? So you have two operations. The first one is what we call as vector addition. The second one will be your scalar multiplication. So your vectors, the set of vectors, when you do your vector addition, then this is an abelian group. So then again, your scalar multiplication concerns with how your field acts with your vectors. So notice the difference. Just now you only have your field elements, and when you specify number 2 until number 6, basically is how your field elements are going to multiply together and how it is going to distribute it across your additions. But now you have two different sets of elements. One is from your vector, another one is from your field. So number 2 to number 5 basically tells you how your field elements is going to be multiplied or interacting with your vector elements. So in this case, when your field scalar multiply with your vectors, it has to be inside your vector again. It has to be associative, meaning that when you have this kind of multiplication, you can just multiply your scalars together. You have one identity. So this identity is your scalar multiplication identity. So where is this one coming from? Is this one coming from your field or this one comes from your vectors?
Field.
From the field. Okay, you need to be careful about this. Basically, this is your identity element coming from your field. And lastly, for bilinearity, basically, if you have vector additions inside, and then you have your field element multiplied as a scalar, then you can distribute inside. And similarly, if you have two field elements, plus together inside, then you can distribute across your vectors. So all these basically you can draw your examples from what you know about a vector space, real numbers and complex numbers. So complex numbers form a vector space over the field of real numbers. The first example of this. So remember when we write complex number, let's say Z, let's say we have R1 plus IR2. So usually how can we visualize this? We draw the Argand diagram, right? So that's actually tries to tell you that your complex numbers actually form a vector space over the field of real numbers. So in this case, your your 1 and I, so 1 corresponding to the real part, I corresponding to the complex part. So these two becomes the basis of your vector space over the field of real numbers. And then your R1 and R2 will be any real numbers. So that's what it means by example 1. Is that okay?
Okay. Wow.
So example 2, the set of all n times m matrices form a vector space under matrix addition and scalar multiplication. So if you want to draw examples, this is a little bit hard, but the most relevant example would be considering your Pauli matrices. So this sort of form your basis for a vector space, even though they are also group elements. It's hard to draw example at this point for example 2, but later on, probably we can try to see how it is. So we all know what is linear independence. So if let's say you have a set of bases and the sum of all these things becomes 0 implies that all your alpha I is 0, then basically this particular set of vectors are linearly independent. So otherwise they will be called linearly dependent. So this is linear algebra. I believe everyone knows this. So if let's say you can find a set of n non-zero linear independent vectors, so let's say v1 until vn, but when you add one more non-zero vectors inside, it becomes linearly dependent. Then it means that your vector space is n-dimensional. So meaning that you try to identify n vectors that are linearly independent. And then when you add in one more vectors and it becomes linearly dependent, then it means that your vector space will be n-dimensional, because when you add in one more vector inside, when you have n plus 1, it becomes linearly dependent. Okay? So then any such maximal sets of vectors, like this particular n vectors of linearly independent vectors, they will be called your basis or your coordinate system. So one of the very good things about vector space, and later on we actually capitalize on this, is that as long as your vector space over the same field, you have the same dimension, they are the same, they are isomorphic. Isomorphic means they are the same. So it doesn't make sense for you to compare, for example, let's say you have R3, which is your, let's say you have your Euclidean space of 3 dimension. And then you also have your spherical coordinate system. Even though your spherical coordinate system is, you try to, how should I put it? You try to emphasize on the spherical symmetry, so that certain physics problem with spherical symmetry, you can easily sort of like write down the equations. It doesn't mean that you cannot do it in R3. So you can always translate between each other. It's just that in R3 it will be a little bit more difficult because you don't have that kind of symmetry. But spherical coordinate system, as long as you are dealing with spherical symmetry, then the equation will be very simple. So it means that as long as you know, for example, R3, then whatever you know on R3, you can apply to your spherical coordinate systems. So this is what it means by they are isomorphic to each other. You can always find a mapping that can map whatever properties of the same dimension of vector space over the same field to the other one. So that's what it means by this. And this is actually really powerful because later on you will see that when we go into representations, you always want to map whatever mathematical objects into your vector space because we know how to deal with vector space. So that's why we study representations as well. So next, what is linear algebra? You can call this linear algebra, you can just call this algebra. So a linear algebra, basically you have, again, two things. You have to define your field, and then you have a set of vectors. So now you have three operations. You have your vector addition, scalar multiplication, and your vector multiplication. Okay. So now your V plus and dot, that will be a linear vector space, which means that it will satisfy all these things. Okay. So I don't want to bother to write down all the axioms. So whenever I say V plus dot is a linear vector space, it satisfies all the previous conditions. Additionally, you have two more conditions that tells you how your vector multiplication is going to interact with your two other operations. The first one is how your vector multiplication interacts with your vector addition. Same thing, just distribute inside. That's called bilinearity. The second one is again closure, meaning that when you do your vector multiplication, it has to go back into your vector space. So now for algebra, you have a little bit more complications because not all algebras satisfy 4 until 7. So number 4 is what we call as associativity. The definition is the same. You have your vector multiplication inside. You sort of like do the first part is the same as do the second part first. This is not always true for the algebra that we study. The existence of identity. So now we meet again this one. Where is this one coming from?
Is it also the field?
Nope. Look at the
Vector.
so the identity is with respect to vector multiplication. Okay. So this identity is not the same as before. The identity over here is with respect to your scalar multiplication, which comes from your field. This will be with respect to your vector multiplication, which comes from your set of vectors. Okay. So you need to be careful a little bit about this. And again, you can have symmetric and anti-symmetric properties under certain exchange. For example, if you switch around this, whether or not you get a plus or minus. So that is your symmetric and anti-symmetric property. And lastly, the derivative property. Okay, this is a bit complicated that I don't want to go into yet. Later on, you'll see an easy version of this. But this is important. So this is important for our purpose because the derivative basically is your Jacobi identity. Later on, we will go into that. So now what will be the examples of your algebra? again, if you look at the set of n times n matrices, just now we know that it forms n square kind of like vector space under matrix addition and scalar multiplication. So now if you introduce matrix multiplication, then this will become associative algebra. So let's say you have two matrices. So usually we just write M1, M2 if they are matrix. So the way they multiply, we know that this is associative, right? With the way we understand how matrix multiplication works, we know that this is true. Okay? So that's why this is associative algebra. Whether or not it satisfies all this, okay, what would be the identity for this matrix algebra?
Identity matrix.
Yeah, it will be your identity matrix. Let's say if it is 2 by 2, so this will be 1, 0, 0, 1. Okay? So this is with respect to axiom number 5. 6 and 7, it depends. So we cannot discuss that at this point. So example number 2. So we can consider the set of real symmetric matrices. What is a symmetric matrix? Basically, it means that when you transpose the matrix, it goes back to the original matrix. But when we try to introduce matrix multiplication, we find that it does not become an algebra because it doesn't satisfy the closure property. So when you try to multiply two matrices together and then you perform the transpose will reverse the direction and transpose everything. And because TT, we know that it is equal to T, ST will becomes S. So this becomes TS. But TS is not the same as ST. So this is not an algebra. So how we can make it into an algebra? By introducing what we call as a symmetrization operation, whereby we specifically design our matrix multiplication as your anti-commutation. Sorry, I think this is this is anti-commutation. So we define this bracket as ST plus TS, and we define what happens when you have something like this. So you just factor out your few elements alpha out, and then you perform this bracket inside. And if you try to test it out yourself using 137, then basically you can show that this thing will become this. So this is for you to show using this definition. I don't have time to show this, but if you want to, you can show. You can try to use 137 to show that this is true. Okay? So if we have symmetrization, then we have anti-symmetric matrices, whereby you perform a transpose, it gives you a minus A. So same thing, now you define a commutator, AB minus BA, and you define how the commutator is going to distribute it across B1 and B2. So you'll find that this is also an algebra. But in general, this thing does not have an identity. Is there any reason why? So it is not associative because when you try to perform the multiplication below, you find that this part does not satisfy, like it's not equal to each other. So A cross B cross C is not equals to A cross B cross C. So that's why it's not associative. But can you quickly identify the reason why in general it doesn't have an identity?
Like it doesn't satisfy A transpose equal to negative A.
Yup, that's the reason. So if you have identity matrix, you cannot satisfy this condition. That's why in general it doesn't have identity. So if let's say you have this kind of algebra with this kind of antisymmetric multiplication defined by 139 and 140, then this is what we call as a Lie algebra. And you need to satisfy an additional condition, which is the derivative property. So now we go into the derivative property. The derivative property basically tells you A multiplied with B multiplied with C equals to this whole thing. This is what we call as a derivation. But in terms of Lie algebra with the commutator defined, is actually equals to 144. So you can consider this as B times C, and then this is A times B times C. And then this is A times B times C. So I shouldn't use square bracket. And then this is B times A times C. So this is based on what we define, okay? But usually we don't really use 144. We use 145, which is called the Jacobi identity. The way to do it is to move these two in front, and then we make use of the property of the commutator. So the commutator between AB equals to minus BA. So then when you switch to the other side, there will be a minus sign. And then for this term, you basically switch around C and AB. For this one, you basically switch around C and A so that you maintain the plus sign across everything. And this is pretty easy to memorize as well. You just need to memorize like the permutation of ABC. So you have ABC, and then you have BCA, CAB. That's why we usually use 145 as our Jacobi's identity. And this is only for Lie algebra. So the next thing that we want to go into is the idea of generators or bases. So the concept will be the same, but in the group setting, we usually call it a generator. So basically for a group, if you can identify the smallest number of group elements, whereby you try to do all the different possibilities of combinations and powers, that will give you all the group elements. So then, so those smallest number of distinct group elements, they will form what we call as the basis for the group. They're usually called by a different name called the generators. So like, for example, if you have P4, what you actually need is something like this. And then switch like this. So you basically just need these two elements, and you can try to generate all the other group elements under P4. if you want to try, just try to use this tool to generate this one. If you want to try, it's not that difficult, but it takes a little bit of practice. So again, going back to vector space, because all the n-dimensional vector space over the same field, they are the same. So you just need to study one vector space, and then you basically know all the properties for n-dimensional vector space over the same field. Okay, so we have what we call as the very standard or canonical n-dimensional vector space. So what we choose usually is this kind of computational basis. Because that's the easiest for us to study. So this will be what we call as the standard computational basis or your canonical basis. So how about for an algebra? For algebra, basically you need to take care of your vector multiplications, and your vector multiplication usually will give you something like this. So this is what we call as the structure constant of your algebra. They will decide what your algebra looks like. So why is it the case? Because if you consider like you have two algebra elements and you try to perform vector multiplication inside, so you will notice that because these two are your field elements, you can sort of like factor them out, and then what is left is your ei multiplied with your ej, and this will go to your structure constant, and this structure constant will determine how your whole algebraic elements are going to multiply together. So that's the reason. I think lastly, I want to go into representation. Sorry.
The summation, the summation should have IJK because I look at the last.
Yeah.
Okay.
There should be K.
Okay.
So this is another typo that I need to modify. Okay. The last one is the idea of representations. So basically, like I said, we want to work with something that we are familiar with. So when we talk about like groups, algebra, and so on, sometimes they are not the easiest for us to imagine or calculate. So that's why we want to sort of like find a maps. Let's say if you have a group, you can map it to some vector space. Then we can work on whatever on the vector space, and we can find the reverse mapping and understand what happens with the group. Okay. So that's the idea of representations. And again, I stressed this a few times already. So whenever you have n-dimensional vector space, you only need to study once, and you can understand all the similar dimension vector space. So for other algebraic objects, then we need to find such a mapping so that we can sort of like map from groups to the vector space and then understand how it behaves under the vector space, and then we can understand what is happening to the group. So this is pretty much similar to when you first study the idea of functions. So you study one-to-one and onto, right? So homomorphisms basically just tells you that it preserves all the operations, but it's not one-to-one mapping. But if your mapping is one-to-one, then that will be the best one, because basically you will be able to map all the properties of your algebraic objects into your vector space. So if it just preserves all operations, we call this homomorphism. If it is also one-to-one, we call this isomorphisms. And if your mapping maps into the set of matrices, and we know that matrices can act with your vector space, and that will be called a representation. So here I will provide a few examples. So the first one will be positive real numbers. So positive real numbers, they will form a group under your multiplication. So what will be the one-to-one mapping to, let's say, vector space? So of course, at this point, you don't really see the matrix structure because it's just one element. So when you try to perform this kind of exponential mapping, you don't really see where the metrics come in. So it's only when you start to look into Lie algebra and Lie groups, then you will see how the matrix comes in. But this will be the easiest example for us to sort of like look into. So again, you have real numbers and you have multiplication. So this forms a group, R plus positive real numbers. So over here, you have multiplication. If we want to sort of like reduce it into addition, then you use the exponential mapping and you define your real numbers as e to the power of lambda. So then you sort of like simplify your multiplication into addition, right? Because you map, let's say your R1, R2 from R to lambda 1, lambda 2 is also in R, but originally this is your R plus multiplication. Now this is your R with addition. So you successfully maps from your multiplication operation into your addition operation. And also, right, you can perform your logarithm on equation 148 to becomes the natural logarithm of R1 and R2. Okay. So then what you are trying to say is basically the multiplicative group of positive number, it will be isomorphic to the exponential of your one-dimensional linear vector space R. Again, right now you don't really see the complications over here. This is a really simple example. Is trying to motivate you why this is important. Later on, when we go into the Lie group and Lie algebra structure, you will also use the same thing. So what will be the complex number version? So we can study complex number with modulus 1. And you can sort of like faithfully represent it using the exponential map through e to the power of I theta. So your theta now sort of like runs between minus pi to pi. So if you have like a group multiplication loss over the left hand side, then you know that they will transform into addition. And what is good about this is actually a lot of the trigonometric identities are derived based on this. Like for instance, if you run this, then you use ei theta equals to cos theta plus I sine theta. Then you'll be able to derive the addition and the addition of two angles of the formula through the left hand side and the right hand side in this way. Okay. So another thing is to help you to find what happens when you take the limits. So when you take the limits, what you need to really do is to add and subtract your group elements. But however, the group that we define is only multiplications. So we can multiply C1 and C2, but we cannot we cannot plus these two together because the addition part is not defined under this group. But with the exponential map, you can do that. So what you need to do is, for example, if you want to find the limits of delta theta approaches 0, so what you can do is to perform your first principle, and then you factor out your ei theta. So at this point, once you did that, I think what you will get is something like this. And then you can sort of like pull out and this will become minus sine theta plus I cos theta. So originally you have ei theta becomes something like this. Then by comparison, you will see that your cos theta becomes minus I sine theta, and your sine theta will becomes cos theta. So through this kind of mapping, you can sort of see that initially you cannot really define your addition and subtraction of your group elements. But because of this mapping, over here, you can use the Taylor expansion to get you this. And once you do this, basically you can sort of like perform the addition and subtraction. And the good thing about this particular mapping also, this exponential mapping, is that it actually relates you with the global properties and the local properties. So the derivation over here is the local properties. We try to study what happens when you zoom into a patch, and then what happens when it looks like when you look at it locally. Whereas over here, 151, it sort of like tells you globally speaking what will happen when you add two angles or two complex numbers together. So 151 tells you the global identities, 153 tells you the local identities. And all these special functions, we especially what you learn in physics for all these special functions, they are actually related to the representations of some groups, even though you are not being taught by your subjects. So that's why it's good if you understand a little bit of group theory, so that you can start to see how it's going to relate together. And I think what else is important? So these two examples sort of like show a very simple, it's sort of like a very simple example to show how the exponential maps is helping you to look at the global and local structures. Later on, when you go into a more complicated group structures, then you will see more about this. So last thing I want to stress on is that this is actually not a special case. This is actually a very general case because your Lie algebra structure is always defining your group. So your X in this case will be your Lie algebra, which tells you the local properties. And then let's say you have some matrix M, which is the exponential of your Lie algebra elements. So this will tell you this is the Lie group, and this will tell you the global properties. So now relate back a little bit to what we already know previously. Your unitary matrix is basically the exponential of your Hermitian matrix, which is a Sumly algebra. And where do you actually see this? You see this in the postulates of quantum mechanics. I forget which one. One of the postulates says that for a closed quantum system, you have your Hamiltonian, and when you exponential your Hamiltonian, it will be your unitary operators. So that's exactly where it comes from. So this is why studying group structure will be a little bit helpful in this case. I think I will stop here for now. Let me stop the recording.